Good day, everyone. Today, we will discuss Topic 6, Rank of a Matrix, one of the most important topics in linear algebra. So, throughout this lesson, we will learn how to determine the amount of independent information contained in a matrix. We will also study the concepts of row space, column space, null space, rank, and nullity, and see how these ideas help us analyze systems of linear equations. So before we begin, let us first look at our learning objectives. So at the end of this lesson, you should be able to first define the row space, column space, and null space of a matrix. Second is to define the rank and nullity of a matrix. Third is state and explain the rank nullity theorem. Fourth, compute the rank and nullity using row reduction. And lastly, apply this concept to solve problems involving matrices. So before discussing rank, let's first understand why it is needed. So matrices are commonly used to represent systems of linear equations and linear transformations. However, not every row or column contributes new information. Sometimes one row is simply a multiple or combination of another row. For example, if one row is exactly twice another row, then both rows describe the same information. Because of this, counting the total number of rows does not always tell us how much unique information the matrix contains. So this is where the concept of rank becomes useful. So rank measures the number of linearly independent rows or columns in a matrix. Another important concept is nullity, which tells us how many free variables exist in the homogeneous equation a sub x equals 0. So together, rank and nullity helps us determine whether a system has one solution, infinitely many solutions, or whether there are free variables. So now, let us define the important terms. First is the row space. So when we say the row space, it is the subspace formed by all possible linear combinations of the rows of a matrix. Next is the column space. So column space is the subspace formed by all linear combinations of the columns. And next is the null space. Null space is the collection of all vectors x that satisfy the equation ax equals 0. Now we define the rank. So what is rank? Rank is simply the dimension of the row space. Since row rank and column rank are always equal, we can also define it as the dimension of the column space. And lastly, nullity is the dimension of the null space. So in simple terms, rank counts the number of pivot columns or independent vectors. Nullity counts the number of free variables. Now, let us study the two very important theorems. The first theorem states that the row rank is equal to the column rank. This means that regardless of whether we count independent rows or independent columns, we will always obtain the same value. The second theorem is called the rank nullity theorem. It states that rank of A plus nullity of A equals n, where n represents the number of columns of the matrix. So these theorems are very important because once we know the rank, we can immediately determine the nullity. So for example, if a matrix has 4 columns and its rank is 3, then the nullity must be 1. So we have here an example. So now let's apply what we have learned. So our matrix is 1, 2, and 2, 4. Notice that the second row is simply the twice of the first row. To verify this, we perform the row operation. So row 2 minus 2 times row 1, the resulting matrix becomes 1, 2, 0, 0. So now we count the number of non-zero rows. So there is only one non-zero row. So therefore, the rank of the matrix is 1. So this tells us that although there are 2 rows, only one contains independent information. Now let us determine both the rank and nullity. So after row reduction, only one pivot remains. Therefore, the rank equals 1. Next, observe that the matrix has 3 columns. So using the rank nullity theorem, rank plus nullity equals 3. Substituting the rank, 1 plus nullity equals 3. Subtract 1 from both sides. Therefore, the nullity equals 2. So this means there are 2 free variables in the corresponding homogeneous system. Now let's solve a slightly more challenging example. After applying Gaussian elimination, the matrix becomes 1, 2, 3, 1, 0, 0, 1, 1, 0, 0, 0, 0. Notice that there are 2 pivot rows. Therefore, the rank equals 2. The matrix contains 4 columns. So applying the rank nullity theorem, 2 plus nullity equals 4, so nullity equals 2. So this tells us that the matrix has 2 independent rows and 2 free variables. And now, it is your turn. For part A, determine only the rank of each matrix. For part B, determine both the rank and the nullity. So remember the steps. First is to reduce the matrix to row echelon form. Second, count the pivot rows to obtain the rank. Third, use the rank nullity theorem to determine the nullity. So you have a few minutes to solve these problems before we discuss the answers. Now let's move to the topic 7, the coordinates and change of bases. In this lesson, we will learn how vectors can be represented using different bases. Even though the coordinates of a vector may change, the vector itself remains exactly the same. So we will also learn how transition matrices helps us convert coordinates from one basis to another. So for our lesson objectives, first is to define coordinate vectors relative to a basis. Second is to explain the concept of a transition matrix. Third is state the important properties of transition matrices. Convert vectors from one basis into another. And lastly, solve problems involving change of basis. Recall that a vector can be written using different coordinate systems. The coordinate values depend on the basis we choose. For example, a point on a map can be described using different coordinate systems, but the actual location never changes. Likewise, a vector remains the same geometric object even if its coordinates change. The process of converting coordinates from one basis into another is called change of basis, and we accomplish this using a transition matrix. Let us now define the important concepts. A coordinate vector tells us how much of each basis vectors is needed to build if a given vector. So if x equals c sub 1 v plus v sub 1 plus c sub 2 v sub 2 plus up to c sub n v sub n, then the coordinate vector simply consists of the coefficients c sub 1, c sub 2 all the way to c sub n. Next is the transition matrix. The transition matrix converts coordinate vectors from one basis to another. The formula shown tells us that multiplying the coordinate vector by the transition matrix gives its coordinate in the new basis. This process allows us to move between different coordinate systems efficiently. The main theorem states that every transition matrix is invertible. This means that if one matrix converts coordinates from basis B to basis prime B prime, its inverse converts them back from basis B prime to basis B. In other words, the inverse simply reverses the change of bases. So this guarantees that no information is lost when changing coordinate systems. So in this example, our basis is the standard basis, which consists of 1 and 0 and 0 and 1. The vector is 3 and 4. Since the basis is already the standard basis, the coordinate vector is simply 3 and 4. No calculations are needed because the vector is already expressed in the standard coordinate system. Now, let's consider a different basis. We are given both the basis vectors and the coordinate vector. First, construct the transition matrix using the basis vectors as its columns. Then, multiply the transition matrix by the coordinate vector. After performing the multiplication, we obtain -1, -1. Therefore, the standard coordinate vector is -1, -1. This demonstrates how transition matrices convert coordinates into the standard basis. Now, let us work backwards. Instead of converting to the standard basis, we are given the standard coordinate vector and asked to find its coordinates relative to basis B. First, construct the transition matrix. Then next, we compute its inverse. And finally, multiply the inverse by the standard vector. The resulting coordinate vector is 3 and 1. This means that the vector can be written as 3 times the first basis vector plus 1 times the second basis vector. So to conclude today's lessons, answer the following exercises. In the first problem, determine the coordinate vector in the standard basis. Second problem, use the transition matrix to determine the standard coordinate vector. And explain why the inverse of the transition matrix converts coordinates back to the original basis. Remember that solving this problem requires understanding both the coordinate vector and the transition matrix. Thank you everyone for listening. I hope today's discussion helped you understand the concepts of rank of a matrix and coordinates and change of bases, and how these ideas are applied in linear algebra.